I'm caught up on the chat. So now we can talk about new stuff. So new stuff. Let's see if we can get this done as far as our discussion by let's our goal be 10 or 10:05 at the latest. There'll be like 3 homework questions that are super simple. You can have it all done before 10:30. I wasn't able to finish. I only okay. Um, Send me an email and we'll get that fixed. Okay, send me an email and we'll get that fixed. Promise. Promise. Okay.
Mr. Wadley,
What's
sorry to
up?
interrupt.
Oh, you're cool.
Could you post the answer key for the review stations we did?
It is posted. If you
Oh, okay.
look on forces on that last day, basically the same page you would have clicked to go into the FRQ. Go below there, and then in all caps, there's a thing called solutions. You click on that, and that will take you in there.
Oh, so that's like where it's like a bank of like all the answer keys, basically.
Yeah, it has a link for each of the answer keys for the review stations, and then also for one of the homework pages is also in there, I believe.
Okay, thank you.
Initially, I didn't think we were going to, but then one of the other teachers went ahead and put it together and published it. So then now it's available to all of us. Um, let's see. Somebody else says my submission refused to submit, so I sent you an email of my work because I don't know if it actually submitted. All right, perfect. Yeah. If anything goes wrong, send me the email because I'll be able to see what you have. And knowing that the email came in within the realm of time of submission or shortly thereafter, I understand. I want to make sure we're doing what's best for you guys and what's right. And if you're showing your work and I have access to it, then it looks like it's all on the up and up and everything's cool. All right. All right. So let's get into the new material so that way we can get through all this. So starting here, we'll have the mass of the planet is 8 times 10 to the 20th kilograms. So it's a big planet. The radius of the planet is 1 times 10 to the 5 meters. So it's a decent sized planet. All right. Smaller than Earth, but it's decent size. And it tells us the acceleration due to gravity on the planet is 5.34 meters per second square. Okay. Now there's nothing to write down here. It's more like, okay, we have a mass, we have a radius, and it tells us the resultant acceleration. Okay. What if I cut the mass in half? What do we think the effect of the acceleration? Okay, this is where I want some interaction. I want you to talk to me. What do we think is going to happen? Don't give me a number, but if I half the mass, will the acceleration go up or down, and by how much? Talk to me.
Up.
All right, so I'm going to shrink the mass. Am I going to have more acceleration or less, and by how much? So if you say up by double or down by half, what do you think?
It'd be down by half.
I think it decreased because when the mass of a planet is increased, the gravity is stronger.
Okay, by how much do you think?
I think it decreased by half then.
Okay. And, if we just kind of are guessing on it too, we can think about, planet Earth compared to the moon. We see images of astronauts on the moon from years and years ago because they haven't gone in a long time. But there was less gravity there and the moon is smaller. So I'm saying if we have half the mass, how does that affect? Okay, we're going to half the mass right now and let's see what happens to the acceleration. It's roughly half. So we went from 5.34 to 2.67, roughly half. Now don't cheat and look at these. All right, so what if I double the radius? Don't go into Canvas and look at these ahead of time. They're all there. But what if I double the radius?
It would double, the acceleration would double because.
Well, isn't it purely based on mass? I don't know.
I don't know. That's what we're guessing. Right now it's a guessing game. There's no penalty for wrong answers. There's just a desire for interaction. So I want the interaction. So if I double the radius, what do we think is going to happen? The mass is the same, but the radius is bigger.
I feel like the concentration of matter in the planet would decrease since the radius is bigger. Maybe that'll affect the acceleration.
But how? What will be the effect?
Decrease?
I think it'll increase.
By how much?
I don't know, but I think the density would go down
let's take a look now. All right, so the mass is going to stay the same, but the radius is going to be doubled. All right, so we're going from 2.67 to 0.67. So what we're seeing here is we are going to be further from the center of the planet because of a bigger radius. Same mass, but now we're further away. So now thinking about an astronaut that's in orbit or that's coming back in, if they're in orbit or if they're further out, they've got no gravity. And as they come into Earth, it certainly doesn't go from 0 to 10, right? So there's got to be some sort of transition. As you're further away, we're seeing less. But now we did what? We doubled the radius, but that change is pretty big. And that change on the order of 4 from 0.67 to 2.67, that's a pretty big difference. And that's more of a magnitude of a 4, a magnitude of 4. Okay. All right. So let's start with, I think this starts with the same planet, or no, the new situation. Let's see if we get it to there. All right, new situation. Here we're going to double the radius. All right, so doubling the radius, what do we expect to see in the, what do we think is going to happen to this acceleration? What value do we think we're going to get if we double the radius?
It'll go down by 4 times.
Down by 4. It's roughly 1/4 by doubling the radius. Okay, let me see what the next one's going to be. All right, what if we half the mass? What do we think is going to happen to the acceleration? Half the
Say
mass.
double?
Half
Oh,
the
half.
mass.
Okay.
It's going to be half
Down
the
by half.
acceleration downwards.
All right, so if we half the mass, the acceleration is 1/2. So now we should start seeing a little bit of what's going on, what the relationships are between the radius, how does that affect gravitation, and the mass, how does that affect gravitation? All right, so now that we have that, let's go on to something else. Let me close that tab and go into this. All right, so this is our formula for acceleration of gravity. So little g is the acceleration of gravity. We know on Earth, little g is 10 meters per second square. That's nothing new. And if it feels like it's new, don't let it, because we've been using that all this time. But how do we calculate little g? Because we're going to go to a new planet and we want to figure out, hey, how is it going to compare? Will we be able to survive? So if we know that big G, or if we're going to be told that this big G right here, this is a constant. This is a gravitational constant. Okay, I'll define that in a second. It's not important right now. Well, we know that the factors that we've seen so far are mass and radius. Where do I put mass and radius into this formula? Where would mass go?
I think next to the constant.
Right, it goes right next to the constant. If mass went up, gravity went up. If mass went down, gravity went down. All right, so then where would radius go?
Denominator.
Pretty easy. There's only 2 boxes left.
On the bottom, but like on the,
Right there?
yeah.
Perfect. Now, we saw that there was a magnitude difference, okay? So this is going to be a power. What power do we think that radius has on the bottom of this equation?
Squared.
Squared, they said with very little confidence. So your acceleration of gravity is your gravitational constant times the mass divided by radius squared. Okay, this is how we calculate gravity. Now, if we're going to calculate the force of gravity, the only difference is now we're going to, in order to go for an acceleration to a force, what do we need to add in? To go from an acceleration to a force, what must be brought into the equation?
The mass of the object.
The mass, right? Because we know that force is equal to mass times acceleration, right? Well, this is acceleration. If we then multiply by another mass, that gets us a force, right? So if I scroll this up, how can we use this information to find the gravitational force between any 2 objects in the universe? Well, we would have big G, which is our gravitational constant. We've got the mass of the large object or planet. We have the mass of the small object, whatever object is in or near or around that planet. And then we're going to divide by their distance between those two objects. And the distance is really the distance between the centers of the two objects. So if you've got two large planets, you're not looking at from crust to crust or surface to surface. You're looking at center of planet to center of planet, or center of person to center of Earth. That's the distance we're looking at, and it's distance squared or radius squared. We put radius because it's going to the center, and it's not just radius of the Earth, like, hey, the plane is in the sky. And when we look at the radius, we're not saying the radius of the Earth to the surface of the Earth. We're saying from the center of the Earth to the surface, and from the surface up to the plane in the sky. Okay, so it's from the center all the way to the center of the next object. Okay, it gets confusing because if I tell you, from the Earth's core to the crust is a certain distance, and then I say I'm 1,000 meters above the crust, you've got to add all that in, right? You've got to add in from me all the way to the center of the planet. But this is your formula, okay? When I scroll this up, you're going to see a little bit more information. Here is your universal gravitation constant. Okay, I don't worry about the units at all because it's not anything to worry about. 6.67 times 10 to the negative 11. That's what you need to remember or write down, right? Your notebooks are accessible during these tests and quizzes. And with a lot of practice problems, it becomes secondhand, 6.67 times 10 to the minus 11. It should be a formula chart value, so it's not something that you have to memorize. Just being good at the formulas and realizing the difference between the force of gravity and the acceleration of gravity. The difference is one mass, okay? Now, the only thing I want to add, and this is also in the notes in Canvas, but I want to walk you through it a little bit, is looking at adjustments or changes. If I were to say, if we changed one thing, how does it affect? That's what we were just doing. We were guessing about it though. But now that we have a formula, we should be able to identify and say with confidence what the change is. So we've got our formula. Force of gravity is the gravitational constant times the mass of the large object times the mass of the smaller object divided by radius squared, or distance from center to center squared. So what happens to the force if the mass is doubled? Here we're looking at the change as it relates to the original force, okay? If I say, what happens to the force if the mass is doubled, we're wanting to know what's the change, okay? If I double one mass. So the technique that I want to teach now is when you're looking at a change, anytime you're looking at a change, in your formula, make everything a 1. Just make it a 1. 1 times 1 times 1 over 1 squared. Okay, everything's a 1. If I change nothing, I have 1 over 1 square, which is 1 over 1, which is equal to 1. So the change is times 1. Nothing changed. That's easy. We kind of knew that already. But what if I were to, let's see, what do we say first? Like doubling a mass? Okay, so one of these ones is a mass. So I'm going to take the mass and I'm going to make it a 2 because I've doubled that mass. Now I have 2 over 1, which is equal to 2 times bigger.
But Mr. Wadley, 1 squared is still 1, so how would it be 2 over 1?
Because it's 1 times 1 times 2 over 1 squared. 1 times 1 times 2 is 2. 1 square is 1. This 2 comes from the top multiplying. This 1 comes from the 1 squared. I said if I double one of the masses, so one of those 1s became a 2. What if I wrote it a little bit differently? Let's see if it's less confusing if I write it like this.
Oh, okay.
So I basically changed one of the masses to a 2. Okay, the next one says, what happens to the force if we triple both masses? Okay, so let's change our answer. Let's erase the answers.
So 1 times 1 times 3.
Yep, so now what we're going to do is we're going to make this a 3 and we're going to make this a 3 because it says we're tripling both masses. If we triple both masses, we have 1 times 3, which is 9, over 1 square, which is 1. And that means the overall force is going to be 9 times bigger. Anytime the question says, what is the change in the force based on changing these parameters, just make the entire equation a 1, all the parameters a 1. Then change the ones they tell you to change and see the effect. Does this part make sense? Okay, we're just simply making all the variables within the formula, g times m over r squared, make the variables 1s, and then plugging in the change that the question indicates. That's if we're changing, we're not going to change big G. Big G's, it's a constant. By definition, a constant doesn't change. We can change the masses, which we've done. We changed 1, then we changed both. How does it affect things when we change the radius? Because when we change the radius, we use the inverse square law. It's the inverse square law because the radius is being squared and it's on the bottom of the fraction, so it's the inverse. So let's take a look at that. I'm going to fix remove these answers real quick. Okay, let's see. Yeah, it does. All right. So what happens to the force when we quadruple the radius? So if we quadruple the radius, that means this 1 becomes a 4. So we would have 1 over 16. So we would have 1/16 times the force. So the force is going to be smaller. The further away you are, it becomes smaller.
Oh, so I see this relationship, right? So as the radius increases, the force of gravity would decrease.
Right. Think about it. The further away from Earth you are, the less gravitational pull it has on you. If you're going out in outer space and you're going further and further away, you're going to perceive no gravitational pull. Now, it may still be there very, very small, but you're not going to feel it anymore like you do while you're sitting on Earth. Now, that's if we quadruple it. I'm going to go through each one of these because I want to make sure that we have this experience for those that are a little bit lost, which is completely fine. We start with 1 times 1 times 1 over 1 squared. Now, what if we change it and we say we're just going to triple the radius, triple the distance? So this 1, yep, and the overall it would be 1/9 times force of gravity. Force of gravity would be smaller. What if it's simply doubled? If we double it, it would be 2 squared, which would be 1/4. What if we were to do 5 times the distance, but double both masses? All right, that's not the one that's on the page. 5 times the distance, but we double both masses. Here, double both masses and 5 times the distance. We would have 4 over 25 times the force of gravity. So we can make changes to either one. All we have to do is plug in the changes that they state. What's that?
Where'd you get the times force of gravity from?
Because that's the effect of the force of gravity. Because what I'm saying is the force of, let me go back. The force of gravity, let's erase all of this. The force of gravity is all based on this equation, right? Oh, come on. Force of gravity is all based on this equation. So if I double a mass and make this 1 into a 2, I'm going to say now it's 2 times what the force of gravity was. The force of gravity doubled. It became 2 times as much. Instead, if I were to double the radius, the force of gravity then would become 1/4 its size, 1/4 times the force of gravity. So if the original force of gravity was 20, if I double the distance, the new force of gravity is 1/4 of 20, or 5. So we're seeing what the change is. The change is that 1/4, and it's applied towards the force of gravity. It's 1/4 of whatever the force of gravity was. So if they gave us a value, we'd say 1/4 of that value. If they didn't give us a value, we would just say, well, it's 1/4 of FG, whatever FG is or was or could be. Does this make sense? this is our entire lesson for today. That's exactly what we wanted to learn is, well, two things really. I'm going to count this as one, being that the acceleration of gravity is calculated through the constant. I think it's 6.67 times 10 to the minus 11, multiplied by the mass of the object divided by radius squared. That's for acceleration. To go from acceleration to force, we know that force is acceleration times mass. So when we put in the second mass, now we have a force, which is gravitational constant, same constant, times mass of big object times mass of little object divided by radius square. We can calculate what the force of gravity is. If the question says, how does the force of gravity change by doubling the mass of an object or tripling the distance from the center of the planet or whatever else, we now have the tools to say what the change would be by making everything a 1, plugging in the changes, then solving this simple fraction, okay? At the bottom of this page, you have access to this page. It's in Canvas. It explains what each of these are. Between now and next class, all I want you to do is number 1, 2, 3, and that's it. You have 3 problems. Class goes for the next, they start squawking over the speaker in about 30 minutes. I want you to look at those problems and I want you to solve them. Before I scroll away from this page, I want to point out one thing. This says 20 centimeters apart, okay, on number 3. If I scroll up, distance is always in meters. I just want to point that out, okay? All right, I'm going to stop this.